Hello everyone, my name is Silvana Trindade and my presentation is about the CQP-RMCSA algorithm, which is a proactive algorithm to reduce spectrum fragmentation in EON-SDM networks. This is an overview of my presentation. First the motivation, then the objective, the CQP-RMCSA algorithm, the performance evaluation, and last but not least the conclusion. So, what are the reasons for this work? Many technologies have been proposed for optical networks to keep up with the increasing traffic of the internet, but recent studies have shown that the traffic in backbone networks will soon exhaust the expanded transmission capacity, even using WDM or elastic optical networks with single core or single mode fibers. To handle this problem, the space division multiplexing technology has been studied, providing enormous increase in the transmission capacity by introducing the space dimension. However, EON-SDM networks have the problem of spectrum fragmentation that happens with dynamic arrival of requests with different teardown times and diverse bandwidth requirements. In this case, the slots are allocated and deallocated dynamically, leading to a state in which there are slots available for allocation but they are scattered along the spectrum, so they cannot be allocated continuously and contiguously to a light path. This causes inefficient spectrum usage and increases the probability of blocking requests. So, SDM supports a high number of spatial modes and can achieve high spectrum efficiency with multiple core fibers, but this technology suffers from crosstalk interference, which decreases the quality of transmission and can block slots for allocation. In this figure, we can see an example of how crosstalk happens when the requests are allocated in the same slot index on adjacent cores. So, considering these problems, our paper introduces a proactive algorithm called core and quadrant prioritization algorithm, the CQP-RMCSA algorithm, to reduce and prevent high blocking caused by the spectrum fragmentation in EON-SDM networks. Using multiple core fibers to evaluate our algorithm, we compared it to the literature algorithms. So, most existing works prioritize slots and cores based on some criteria that limits their allocation to some type of request. For example, assigning a kind of request for each core based on the bandwidth requirements. The idea behind the CQP-RMCSA algorithm is to define sections of allocation, but to have no restriction on which requests can be allocated on each of them. The CQP-RMCSA algorithm divides the spectrum into quadrants, each comprising non-adjacent cores and a subset of their slots. We define this order offline. This way, the only online overhead is the search for available slots in the ordered list. To explain better, I'm going to first explain both criteria. So, first is the core prioritization. In the core prioritization process, each core is a node in a graph without any connections. Next, each core is connected to their adjacent cores, where the weight of each edge is the physical distance between cores, forming a graph G. Then the complement of the graph G is generated, considering the same metric to the weight, forming the graph GC. Then we selected the node N with the highest degree in GC. If there are multiple nodes with the same degree, we select an arbitrary node N among them. Then we select an adjacent node with the highest distance, which is also not adjacent to the predecessor node. If no nodes satisfy this criteria, then the algorithm just selects a node with the highest distance. Node N becomes the predecessor node, and the selected node becomes N. If there is any node without priority, the algorithm continues to execute. Lastly, the algorithm adds the priority queue all nodes in GC with degree 0. Now let's look at the quadrant prioritization. In this figure, we can see a 7-core fiber, where the matrix represents the multiple core fiber, divided in quadrants, available slots in white. The CQP-RMCSA algorithm divides the spectrum into quadrants. The cores that comprise a quadrant follows the core prioritization criterion, which defines an order for allocation that generates the lowest possible crosstalk. The quadrants are also ordered so that the allocations in one quadrant generates the lowest possible crosstalk onto the slots in the next quadrant. So, both the core and quadrant prioritizations are defined offline. So when requests arrive, we need an RMCSA algorithm that can use these criteria for spectrum allocation. First, the CQP-RMCSA algorithm finds k candidate paths. After that, the algorithm tries to find a block of available slots in each path using the flood fill algorithm. But since we have a quadrant prioritization, the search is performed only inside a quadrant. The search is only performed on the next quadrant if no block of available slots were found in the previous one. To assess the performance of our algorithm, simulation experiments were employed and results compared with other algorithms. For each simulation, 100,000 requests were generated, and simulations for each algorithm used the same set of seeds. Confidence level is 95%. The allocation process considers different modulation formats and different crosstalk limits. For the simulations, we used the NSF-net topology and the USA topology. The NSF-net topology has 14 nodes and 21 fiber links, whereas the USA topology has 24 nodes and 43 links. In the simulated network, each channel has 7 cores, and the spectrum is divided into 320 frequency slots of 12.5 GHz each. So, we consider the bandwidth blocking ratio and the network fragmentation ratio as the metrics to evaluate the algorithms. So we compared our algorithm to the first core first fit algorithm and partitioning and core prioritization algorithm. The first core first fit algorithm selects both core and slots in ascending order and uses the k-shortest path algorithm to select routes. The PT algorithm divides the spectrum into areas, considering the number of slots, and uses its own core prioritization technique, which is different from ours. The PT algorithm group requests by their bandwidth and maps each group to a specific core. So, these figures show the results for bandwidth blocking ratio. In the NSF-net topology, the PT algorithm starts blocking underloads of 75 lengths, while the CQP-RMCSA algorithm starts blocking only underloads of 175 lengths. For the USA topology, the FCFF algorithm starts blocking underloads of 25 lengths, while the CQP-RMCSA algorithm starts blocking underloads of 150 lengths. The CQP-RMCSA algorithm produced the lowest BBR values under all loads considering both topologies. Here we can see that the PT algorithm, by limiting the areas where a request can be allocated, can hurt the network performance, due to the fact that the area might be full and the requests are rejected, while there could be plenty of room for allocation in other areas. So the CQP-RMCSA algorithm also does core prioritization, but does not impose such limitations. Instead, it only specifies an order that helps avoid crosstalk. The results, as we can see, in the algorithm only starting to block much later and being able to keep much lower rates in blocking. These figures show the results for network fragmentation ratio. In the NSF-net topology, the CQP-RMCSA algorithm produced the lowest fragmentation values compared to the FCFF algorithm after loads of 50-year lengths. In the USA topology, after loads of 125-year lengths, the CQP-RMCSA algorithm produced the lowest fragmentation values compared to the others. Similarly to the BBR, the order created by the CQP-RMCSA algorithm helps avoid crosstalk generation, especially under low traffic loads. The results show that reducing the incidence of crosstalk, the fragmentation in the network is also reduced, leading to a conclusion that crosstalk has a significant impact on fragmentation. The results evince that combination of strategies to allocate slots decreases the spectrum fragmentation and increases the probability of request acceptance. So, to summarize our work, we introduced a proactive algorithm to prevent spectrum fragmentation, resulting in less blocking and fragmentation ratio. The CQP-RMCSA algorithm employs both core and quadrant prioritization, determining and ordering to allocate slots. Analyzing the results, we conclude that crosstalk has a strong impact on fragmentation. Techniques that do not put an emphasis on crosstalk during allocation were outperformed by the CQP-RMCSA algorithm, employing a rather inexpensive approach in terms of computation, thus proving that our proposed solution to organize the light paths on the spectrum is effective. Thank you.